Alright, hey everybody, we are talking about factoring. Now, I do want to connect factoring with our multiplying polynomials from our last video. What we are going to actually have is a quadratic expression, something like this. And it is our job to put it back into two binomials, and that's what factoring is. Now, if you remember, when we were multiplying polynomials, we were going the other way. We were given two binomials, and we had to FOIL or use the distributive property to get the quadratic expression. So, for example, this is actually x plus 2 times x plus 3. Because when I multiply this out, let's do this. We can do FOIL or box for our organization method on our distributive property. So x times x is x squared. X times 3x is 3x. 2 times x is 2x. And 2 times 3 is 6. So then when we add our like terms, this is a 5x. So we would get x squared plus 5x plus 6. So we are actually going in the reverse direction. We are going to be given the quadratic expression and trying to find the two binomials that you see here. Whereas in the previous video, we were given the two binomials and we had to work our way to the quadratic expression. So that's where we will be headed. Today our main focus will be on factors and greatest common factor, and then we should move on to factoring in this example that you see here. Alright, so which of the following of these are quadratic expressions? Quadratics have the highest exponent of a 2. So if we take a look here, this is a quadratic expression. That's because the highest exponent is a 2. Looking at this one, x to the third, it is not a quadratic expression because it has a cube. This is actually a cubic. And then we have x to the fifth is not a quadratic. X squared plus 9 is, and 1/2 x squared minus x is as well. Because the highest exponent of 2 in all three of these cases, all three of them are quadratic expressions. Alright, so there's a couple of vocabulary words. The standard form of a quadratic is x squared plus bx plus 6. The factored form is x plus m times x plus n. So we have some number here and some number there. So if you went back to the first slide, this over here is my standard form. And this over here was my factored form. So we are used to having the factored form and then multiplying by the distributive property to get the standard form. Factoring is all about going the other way, going from standard form to the factored form. Now a prime, remember a prime number is any number that can only be multiplied by itself and 1. So if I look at it, 7 is a prime number because the only way I can multiply two numbers to get 7 is 7 times 1. Now 4 is not a prime number because I can multiply that by 2 times 2. Notice it's also multipliable by 4 times 1. Because I have multiple sets of factors, 4 is not prime, but 7 is. So let's talk a little bit more about factors. Well, what are they? Factors are a set of two numbers that can be multiplied into a bigger number. So, for example, what two numbers multiply to 50? Well, there are several examples. 50 times 1, that's a set of factors there. 5 times 10 is another example. 25 times 2. And then you also have a set of negatives. Negative 50 times negative 1. Negative 5 times negative 10. That's a multiplication symbol there. And negative 25 times negative 2, because remember, two negatives multiply to a positive 50. So why don't you try right now, pause and give me the factors of 6. Alright, so we have 3 times 2, we also have 6 times 1, and we also have negative 3 times negative 2 and negative 6 times negative 1. Alright, but what does factoring and greatest common factor mean to us? Now, greatest common factor, remember, common means it's shared by something, and greatest means that it's the largest. So when I say GCF, I want you to automatically think of greatest common factor. So first thing I want you to do is find the factors of 16 and find the factors of 24. So we have 4 times 4, we also have 1 times 16, and we also have 2 times, 2 times 8. Over here for 24, we have 6 times 4, 8 times 3, 2 times 12, and 24 times 1. It's very important that you get all the factors, otherwise you will not have the greatest common factor when you go to solve this problem. So I look at the factors of 16 and the factors of 24, and I notice they share several numbers. They're both divisible by 4, and they're both divisible by 8. Here's where that word greatest comes into play. While they're both divisible by 4 and 8, you want to choose the biggest. So the greatest common factor of 16 and 24 is 8. All right, why don't you try it with 36 and 6? All right, so when you did your factorization of 36 and 6, you should have noticed that the greatest common factor that is shared by both is 6. All right, so sometimes it's easy to see, but if not, what we can do is called prime factorization. And prime factorization actually breaks it down into prime numbers. So 24 would be the result of 2 times 2 times 2 times 3. You'll notice that 2 and 3 are all prime numbers. That's why we call it prime factorization. 52 would actually be broken down into 2 times 2 times 13. Again, all prime numbers. So what I notice is that they both share 2 2's, so the GCF here will be 4. So let's try that with 180 and 70. You can go about this several ways, but I like to do it where I divide by 2 if it's an easy even number. So 90 times 2, and then I can break 90 down into 45 times 2. Now 45 is not even, however I can break it down into 5 times 9, and then 9 can be broken down into 3 times 3. So all the prime numbers here, if I were to break down 180, it would be 5 times 3 times 3 times 2 times 2. That is going to be equal to 180. All right, I want you to try the same thing with 72 right now. All right, so now that we have our prime factorization for both 72 and 180, what we can do is circle what is shared. I see that 72 and 180 both have a 2 as a prime factor. They have another 2, and they have a 3, and they share another pair of 3's. So the GCF will be 2 times 2 times 3 times 3, which is 36. Now, occasionally we'll come across numbers that are called relatively prime. The number 15 is not prime, and the number 28 is not prime. However, when I do my prime factorizations and break these two down, you'll notice that they do not share. There's a 2, and a 7 is not shared by the 3 and the 5. 15 is equal to 3 times 5, but 28 is equal to 2 times 2 times 7. They don't share anything, so they are called relatively prime. All right, so what's really important here is how do we find the GCF of variables? So what we have is x to the 4th and x to the 3rd. We know that x to the 4th is x times x times x times x. We know x to the 3rd is x times x times x. So again, we circle what is shared by both, so the GCF is 3x's or x to the 3rd power. So let's do some examples, all right? We have x squared y, so this would be x times y. Over here would be x times y times z. So we begin by circling what is shared. I have a pair of x's on both sides, and I have a pair of y's on both sides. So the greatest common factor here will simply be x times y or xy. So what does this mean for us as far as factoring goes? So remember that we're going to have quadratic expressions, and we need to factor each term of the polynomial and see if there's any GCFs. So for example, there is a 4x squared, which when I do my prime factorization, I get 2 times 2 times x times x. And when I do the prime factorization of 8, I get 2 times 2 times 2. Notice that 4x squared and 8 share 2 4's. So the greatest common factor will be 4. Now, what this means is I'm going to take each term, 4x squared, and divide it by the GCF 4. So 4x squared, I'm left with x squared. Negative 8 over 4 is negative 2. I put my GCF out front, and that is my final answer. Basically, I can double check my work, redistribute the 4 in, and I will get 4x squared minus 8. Alright, for 6x squared, 3x, and 30, please do the prime factorizations and then restart the video. Alright, so these are the prime factorizations for the three terms. I noticed that they all share a 3, so my GCF will be 3. So by pulling out a 3, okay, 6x squared divided by 3 will be 2x squared. 3x divided by 3 is just 1x, and negative 30 divided by 3 is negative 10. You will always check GCF first and to see if you can pull out a factor before we go into the really big factorings. Alright, do the prime factorization for these two numbers, 12x squared and 2x, and then I want you to go ahead and complete the entire problem. Alright, so for this problem, I'll have a GCF of 2x. So I put 2x outside of a parentheses. 12x squared divided by 2x will be 6x. 2x divided by 2x is simply plus 1. The most common times when people make a mistake is they'll forget to leave a plus 1 there. You need to be able to multiply the 2x back inside to get the problem that we started with, to get the standard form. Alright, so there are going to be some 3 questions here that I would like you to try for you try problems, and this will end the video for today once we go over these 3. Alright, so we share 2 2's here, 2 2's here, and 2 2's here. We share an R all the way across the board in all 3 terms, and we share a T in all 3 terms. So we have to look for the GCF in all 3 terms for this one. So it would be 2 times 2 times R times T, which is 4 RT. Oh, wait, I forgot. There's an S for all of them as well. So it's actually R times S times T, which is 4 RST. Okay. Now the division here gets a little confusing, but I want you to take a look. When you do the prime factorization, the GCF is 4 RST. Notice that I did not circle certain things. That's because when I divide 8RST to the third by 4RST, I'm left with the 2t squared, the 2t squared. So that's another way to check, which means that this second one is going to be a negative RS, and the last one is going to be 2 times 3, or 6. There's 2 remaining R's and 3 remaining T's. Okay? So you can always check and see what's left over, and that will appear in the factored form. Alright, so for this last one, we have 13x squared as our GCF. We only have x remaining and a plus 3 remaining, and that's it. And remember that you can check and see, what do I have left over? I have an x and I have a 3, so an x plus 3. Alright, that's it today for GCFs. We will begin tomorrow with difference of squares. I'll see you later.